Okay, let's see if I can solve 12-14 here. Mixture of total composition given here at equilibrium at 160, 250 psi. Wants to know the compositions of gas and liquids. Use equilibrium ratios from Appendix A. So that's the K tables in the back. So here this is. This problem is basically the same as the example problem. Let's see which one it is. It's this one, I believe. Yeah, example 12.4 plus they kind of sneak in 12.5. You need to know that as well to solve this problem. So the first thing I do is create a spreadsheet. I already solved the problem here. I'm just going to walk you through it. So here's our components. Here's the mole fractions, or Z, of each component. This is just from the table. So basically we need to go look up the K factor for pressure of 250 psi, temperature 160 for each one of these components. I went ahead and cut and pasted those in this spreadsheet. So we would go to 250 psi, which is roughly in here. These tables are really bad to read. And this would be the 160 Fahrenheit line in here. We would come over and read a K value of 1.1234 or something. So I guess that it was 1.335, close enough. It's really hard you can't read it to within accuracy much better than 1/10. So there's that value, and then you need to find a K factor for butane. You go to the butane chart, which is A-5, same deal, 250 psi, come up to the 160 Fahrenheit line, come over here. We're at basically 0.1234, 0.55 or something like that. Oh, how about 0.6? Close enough. And the pentane value, go to the pentane table, same thing. 250, come up to this line, come over, so it's 0.1, 0.2 something. How about 0.30 something or another? Close enough. Basically, I want to confess that I used NIST reference properties, which is a fluid property calculator, to calculate these K values, which basically has the equations of state for all this in it and can calculate exact values instead of using these tables. So that's my confession. These are actually equation of state values that I calculated somewhere else. But you can see you can get roughly close on the K value charts. So the next thing you want to do is you want to do Z times K. So create you a formula that multiplies Z times K for each value. Copy those down. This should be greater than 1 if you are going to have some kind of mixture. If it's less than 1, go back and read the book. You'll understand that. Same story with Z divided by K. So Z divided by K, you do those values, create a summation of those. That should be greater than 1 for you to have a mixture. If you don't, if it's less than 1, you don't have a two-phase mixture. You either have liquid or gas. So we did that little checking component and confirm that we do have a two-phase mixture. Now we need to calculate one of the phases. That requires you to guess a value. So for this one, just so I can show you how it works, let's have guessed a value of 0.4, which is not correct. So we need to calculate, this is the formula, so it's Z divided by 1 plus NL times 1 divided by K minus 1. That's the formula from back over here in the book, wherever that's at. Back here in the book, you can see those formulas. Here's showing the formula right here. This guy right here. So we would need to guess a value of N sub L. Let's guess 0.4. And you copy that all the way down. This needs to add up to 1 for it to be the solution. This is an iterative process. I use the solver. You can use trial and error and guess 0.42. Keep guessing 0.43. See, we're getting closer to 1. What if I guess 0.6? We're right at 1 with 0.6. That's a pretty good answer. If you didn't know that well and we wanted to use the functionality, if you go to Tools and Goal Seek, find Goal Seek however you do it in your Excel, we want to set, let's see, we want to set this cell to a value of 1 by changing this cell, and then it will run. There's our solution. It was already there because it's basically 0.6. So 60% of this mixture is liquid, 40% of the mixture is gas, 1 minus 0.6. And then to have these values, we can divide and find these values. So these are your compositions. Here's your liquid phase. 57% of the liquid is propane, 35% is butane, and basically 7% is pentane. And over here would be your gas phase. So if you wanted to know the actual densities and whatnot, you can calculate that out. But this is what the question's asking. Here's your liquid composition, gas compositions, and here's the overall liquid and gas composition, basically 60-40, which sounds pretty good because I think he planned it to be that way. So that's the solution to 12-14, more or less.